Alrighty folks, in this video we're going to be talking about sets. So sets you may have seen introduced somewhere in high school math. This is also a very big concept at the start of an abstract mathematics class. So we're going to be talking, kind of defining what a set is, where it's used, and kind of what it means overall. Right? So just a general breakdown. What are sets? So sets is essentially a more advanced version of counting. So essentially, sets are just a collection of values. So they don't necessarily have to be numbers. Oftentimes in math, they are numbers. But so it uses this sort of notation here. So before we get into that, let's just look at kind of a collection of numbers here. So let's take this random collection of numbers. Let's say we have 2, 4, and 8 here. Okay, great. So these are just some numbers we have here. So this is just a collection of numbers. So we can define this collection of numbers here to be a set. And essentially all that's doing is we're saying this is a set of values here. So we use this kind of set notation, which is that little curly brackets that we see there. So that's how we kind of define a set. But again, this is almost to be interpreted as just kind of a list of numbers. It's a collection of values here. So as I mentioned before, sets don't only have to contain numbers. They could contain other things. So because of that, we stray away from calling each value in our set to be numbers. We have a particular name for them. So here we call them elements. So we say that they're elements of the set. So here in this example, I have a set with 3 elements, and those elements are 2, 4, and 8. So it's a set of 3 elements, and it's described this way. So now I'm going to give an example of what I mean by elements of set. Can be things other than numbers. Right? So let's say we have some other set over here, and we're talking about this set, which is the set of, let's say, 1, 3, and the third element of this set, let's say it is the set 2, 4, and 8. Okay. So sets don't only have to have 3 elements. I'm just giving some examples here. In this case, they both have 3 elements. But so the set on the right has 3 elements in it. Right? So those elements are 1, 3, and this set here. Right? So this set here in this example is an element of this entire set. Right? So kind of have a larger set here, and this set can be an element within another set. So the larger set contains elements 1, 3, and the set containing elements 2, 4, and 8. This would be different than, say, the set containing values 1, 2, 3, 4, and 8. Right? So these are different sets here. Right? So it's different. So it's kind of, it's a little difficult to think about, right? But this is kind of how we define sets to be. So this is just an example of how sets can contain elements that are not necessarily numbers. So that's why we have this special name to them called elements. So lastly here, we're going to be talking about some particular sets that are of interest to us, particularly as we're looking kind of as an intro to abstract mathematics. So, as I said before, sets can contain more than just 3 elements, right? They can contain many elements. They could contain 10. They can contain just one element. Sometimes they can contain no elements at all. That's an interesting one. Sets can also contain an infinite number of values, right? So they don't have to be just finite. They can contain more values than are possible to count even. So an example of these, one of the more basic examples, would be our set of natural numbers, which we define using this, what we call a blackboard bold N. So this is our set of natural numbers. So the set of natural numbers, this is kind of also known as our counting numbers. It's also known as our counting numbers. So this would be our numbers starting from 1, right, 2, 3, 4, and so on, right? So this would continue on here. This is an infinite set, so obviously I can't write everything out here, so we kind of use those 3 dots there to indicate this continues on in this pattern here. So this would be an infinite set of natural numbers. So if we looked at kind of how many elements are in that set, we would say that it would be an infinite number of elements in that set. Likewise, expanding on the natural numbers, we can look at our set of integers. This is given by a blackboard bold Z. Kind of an odd notation choice for this, but this is our integers. This is our integers. Interestingly enough, so the integers expand infinitely like the natural numbers do, but the natural numbers are infinite in one direction, right? So we have a starting point at 1, and we go infinitely greater in the natural numbers. Integers are different than that. They're actually expanded infinitely in both directions, right? So integers include 0 here, and of course it includes all of those natural numbers, and so on. But it also includes every negative number, so we can kind of almost count backwards here as well. -1, -2, and so on. And so we see here that the set of integers is kind of negative in both directions. One interesting thing to point out here, many folks might assume that since the set of natural numbers expands infinitely in just one direction here, right, it has a starting point and then kind of goes, whereas the integers expand infinitely in both directions, one might assume that there's more elements in the set of natural numbers than there are elements in the set of integers. That would actually be false. So they both contain an infinite amount of numbers, and so as such, they're actually the same size, which is really quite interesting to think about. If folks would like to see a video explaining that idea, I'd be happy to do a video like that. Just let me know in the comments section down below if you'd like to see that. So last set here I'm going to define for everybody is a set of values that you might use more regularly, especially in a proof class. This would be our set of real numbers. Set of real numbers kind of includes most numbers that you can imagine and think of. So of course it's kind of hard to represent the set of real numbers because it includes every value that are included in the integers, but also includes every fractional value. It includes every decimal, which is including decimal values that are repeating, but it's also including decimal values that do not have an n. So this also includes, right, pi. So pi is in with the real numbers. So is any other value. So is any other fraction like this as well, right? So basically any value that's not an imaginary or a complex value will be included in the real values that we see here. Also, interestingly enough, the set of real values, you'd think, so obviously this is an infinite set. However, this actually is a larger infinite set than the set of natural numbers or integers, right? So the set of real numbers is kind of a larger infinity than the other infinities given by the natural numbers or integers. So pretty interesting concept. If folks would like to see an explanation of that, again, please let me know in the comments section down below.